Well, hello everybody. It's the bonus quiz for 7.5, and they're asking us here to add and simplify by collecting like radical terms if possible. Now, what's happening here in the course is we've had so much math that we're starting to see the same ideas getting recycled and decorated up in a slightly different context. And that's what's happening here. If I gave you this problem, 3x plus 2x, you would immediately, without thinking, combine like terms and say 5x. What's going on there is really, though, it's sort of interesting if we look beneath the scenes. 3 times x, 3x, is really a bunch of addition. It's saying add together 3x. And then I have this addition sign, and then I have two more x's. So written out in longhand style, this left side is just this. If I go back to multiplication, though, we have how many x's? Well, we have 5 x's. And so that's what's going on when you add like terms. And it's really no different. It's the same idea when you have this situation. 3a plus 2a, you'd say 5a. 3 radical 2 plus 2 radical 2 is obviously going to be 5 radical 2. And I could make the same argument here as I did with the letter a. We don't straight away see that we have like terms here, and so we need to manipulate these. And 81, I pull it out. Now we're looking for cube roots here, so I'm going to be looking for triplets inside 81. And I see 81 is equal to 9 times 9, and each of these 9's is equal to 3 times 3, and so the prime factorization of 81 is 3 to the fourth power. But I'm not going to quite write it that way. Since we're taking the cube root and we're looking for triplets, I'm going to write 3 to the fourth like this, creating a triplet, like so. And then we have an addition of another term, which is 24. And I don't see any triplets right away there. So I pull it out and I tear it apart into its prime atoms. And 2 times 12, 2 is prime, but 12 is not. 2 times 6, and 6 is 2 times 3, and that's all she goes. And so 24 is equal to 2 cubed times 3. And the cube root here of 24, written in terms of triplets, is going to look like this. 2 cubed times 3. Now the idea there, of course, is the cube root will undo all of these cubes in each of these cases. And those cubes will come out as a multiplier. So this cube root will undo this cube, and the 3 will come out as a multiplier. And what got left behind is just the cube root of 3. And it's the same game here. This cube root will undo this cube, and the 2 will come out front as a multiplier. And what got left behind is simply the cube root of 3. And now I see I have 6a's plus 2a's. Clearly I have 8a's. And the a in this case is the cube root of 3. And that is the answer to this problem. I have simplified it by collecting like radical terms. 8 times the cube root of 3. And we'll move on to the next problem, which is a situation where we're going to rationalize the denominators. And this is a move that you'll see quite a bit in trigonometry and calculus. In fact, it's really the only reason why you're learning it here is to prepare you for those courses. And it's built on this idea of what they call a conjugate. Now, you should be very used to seeing this. Again, we're recycling these ideas, dressing them up in new context. And in this context, we're not calling it the difference of two squares. Remember when we had two binomials that were identical, except for the signs here, that it could be multiplied out quickly as the difference of two squares. Or vice versa, if you were given this, you could factor it like this instantly. And that idea was called the difference of two squares. The shortcut for multiplying two binomials that are identical, let's say two bicycles that are identical except for the pedals, was to simply square the first term and then subtract the second term squared. First term squared minus the second term squared. And the reason for that is because every time you multiply this out with your FOIL or double distribution, every time you get a plus BA and a minus BA and they cancel. And all you're left with is A squared minus B squared. So that's the origins of the shortcut. And the idea here is that we're going to take this fraction and we want to get rid of this radical. We want to rationalize. We want to make all rational numbers in the denominator. This is an irrational number. And so we have 7 minus the square root of 6. We think of it as a binomial. And we find that we multiply it by its conjugate. which is just, this idea. And or if you have minus, the conjugate would be this with a plus. Here I had a minus, and so I find the conjugate with a plus. Of course, you don't multiply just the bottom of a fraction. You have to multiply the top of the fraction to maintain the ratio. Or if you will, you're just multiplying by 1 here. And so what happens on the top is this. We have this distribution to do. And I'm only doing that because that's the way MathXL wants this entered into the computer on top instead of the factored form. I prefer the factored form. Most math teachers would leave it in factored form. But we will obey the dictates of MathXL and do the multiplication. Now on the bottom, remember, it's just going to be the first term squared minus the second term squared. The first term squared is 49 minus the second term squared, which is radical 6 squared. Now for me, that's immediately going to be 6, but if you don't see that, you have this situation. Radical 6 is the number that times itself is equal to 6. So lo and behold, we get 6 down here. And notice the denominator no longer has an irrational number. It's completely rationalized. On top, we have 28 plus 4 radical 6. And on the bottom, we have 43. And nothing here will ever cancel because 43 is prime and can't be factored. We need to create a fraction, and we have 28 plus 4 radical 6 all over 43. And let's do a submit. So there you go. Question 1 dealt with just collecting like terms, but it was dressed up differently. There were radicals. Question 2 was really just the difference of two squares, but they're calling it a conjugate. And you use the conjugate to eliminate the denominator, in our case, or the numerator, of irrational numbers. So there you go.